Sorry about that. On that unit circle, every B prime point is referred to as a terminal point. It's the end point of that arc. It's the other end point. The B is always going to be at 1, 0. Okay, that's always that ordered pair. But B prime is going to change. Every ordered pair for B prime should satisfy the condition x squared plus y squared equals 1. But there's some on here that are really nice. Obviously, if I change my rounding here to maybe 15 decimal places, okay, you see that this y value is really nice. The x value kind of stinks, but we're going to find out that it is this number here. But all the other ones, I mean, look at those black numbers. Those are pretty ugly, and they don't turn out to be real nice things, okay? And I'm just changing by 5 degrees here every single time. But we do end up with some situations where we get really convenient values for our ordered pairs. And this is one of them, okay? And I want to kind of explain to you what those convenient values are and where they come from, and where essentially the unit circle comes from, okay, and the information that we're going to have on it. Right there, that green angle is 30 degrees, right? Now, if it was in radians, it'd be pi over 6, okay? But let's use it in degrees, because it doesn't matter in regards to what we're going to do here, whether we're in degrees or radians. If I were to take from B prime and drop a line that is straight down to the x-axis, that should be perpendicular, right? What kind of triangle did I just create? 30, 60, 90 triangle. Okay? Now, in every 30, 60, 90 triangle, she'll pull it out here to make it a little bit easier to see. In every 30, 60, 90 triangle, we have talked in geometry how there is a relationship that is 2n, this is n radical 3, and that is n, right? Okay? And all of those things, guys, are generated from basically taking a larger isosceles triangle, or I guess equilateral triangle, where this is 2n, this is 2n, and this is 2n, and drawing down that altitude that exists and trying to work through essentially your Pythagorean theorem to find this n radical 3, and that's always going to work. Okay? So this is all because of Pythagorean theorem. Well, right now in the unit circle, this 2n is that distance right there, isn't it? So it's what? 2n should equal 1. So if 2n equals 1, can I solve that equation for n and get 1/2? And then come down here and say, well, n times radical 3 would be radical 3 over 2. And now let's put that picture back over top here in the unit circle. It means that that distance right there, from A, let's call that point D, from A to D is radical 3 over 2. From D to B prime is 1/2. That's the x value and the y value to go from A to B prime, right? So does it make sense that that ordered pair has to be radical 3 over 2 times 1/2 that describes B prime? Okay. So that's nice. Okay, it's really nice because 30-degree angles show up a lot in the stuff that we do. 60-degree angles show up a lot in the stuff that we do. Looking at, I didn't mean to do that. Looking at a 60-degree angle. Does that triangle still exist here? This is 60 now. Now that's 30, and this is still 1, right? So the 1/2 would be now the x distance, and the radical 3 or 2 would be the y distance, and that's where we're seeing that ordered pair kind of flip positions, right? Okay. Let's kind of talk about how this is very similar to what we've already done in Algebra 2 and college algebra. I'll put in the line y equals x. Okay. If I have a 30-degree angle, it's right there. If I have a 60-degree angle, it's right there. Aren't those points B prime there and B prime there? Aren't there reflections across the line y equals x? And if the reflections across the line y equals x, doesn't that mean that their x and y's switch spots? That's exactly what's happening. Now there's another angle that's really convenient for us, and it's that one there. Okay, you have a 45-degree angle. Well, let's think about, so this triangle here would be a 45, 45, 90 right triangle, right? We have talked in the past that in a 45, 45, 90, that's n squared plus n squared should equal this side squared, right? Solving for that side would give you n radical 2. Your hypotenuse is always radical 2 times as long as a side in a 45, 45, 90 triangle. So here in this picture, my n radical 2 is 1, right? Solve for n, you would have n is equal to 1 over radical 2. If you rationalize that, n ends up being radical 2 over 2. Does that make sense, everybody? So then, going from A to B prime, those coordinates, that would be radical 2 over 2, and I would travel in a y distance of radical 2 over 2, and I get to that point. Does that make sense? There's another way of proving that that should be radical 2 over 2. What is the equation of the circle? X squared plus y squared equals 1, right? What's the equation of this line right here? Y equals x. If those two things cross, which they do right there and right there, correct? I should be able to use these two equations in a system to solve for their intersection point, right? Now, this is what we call a system of nonlinear equations. And when we have systems of nonlinear equations, we like to substitute. Can I take y equals x, and everywhere I see y up here, replace it with x? Okay, so I have x squared plus x squared equals 1. That'd be 2x squared is equal 1. That'd be x squared equals 1/2. Okay, that'd be x equals plus or minus radical 1 over radical 2, right? Well, radical 1 is just 1. And 1 over radical 2 will rationalize to that, right? So we see that x is plus or minus radical 2 over 2. Well, the plus would be that version there, right? The negative radical 2 over 2 would be the point for x down there, right? Or the x coordinate for that point down there. Okay? Now, if y equals x, and I just said x was radical 2 over 2, doesn't y have to be radical 2 over 2? Does that make sense to everybody? So there are some points on here that are going to be very, 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 very useful for us if we can remember that for an angle of 30 degrees or pi over 6, we have the order pair radical 3 over 2, comma 1/2. For 45 or pi over 4, we have radical 2 over 2, comma radical 2 over 2. And then for 60, we have that. Okay. For 90 or pi over 2, you see the order pair there? Is that a nice, convenient order pair to know? Is that a nice, convenient order pair there to know for pi? Right there? Negative 1, 0. 3 pi over 2, 0, negative 1. And then 2 pi disappears, but 2 pi is going to be 1, 0 again. Okay. So let's get to the PowerPoint, the PDF for a couple minutes here. We did example 1 last week. Let's do, let's kind of skip example 2. I think you guys can be able to do that. Basically what you're going to do is, if it satisfies the unit circle, we'll do it. Go ahead, let's do this quick. If it's going to satisfy the unit circle, it's this, right? It's going to fit that equation. Do you know the x-coordinate? Looking for the y-coordinate, right? What's radical 3 over 2 squared? What's radical 3 squared? 3, what's 2 squared? Okay, can I subtract 3/4 from both sides? So y squared is going to equal 1/4, right? Can I square root both sides? Plus or minus 1 over 2, correct? So I got to choose, and if they didn't give me other information, I would go with both those answers. Because both those, the point radical 3 over 2, comma 1/2, and the point radical 3 over 2, comma negative 1/2. Think about this. If that's plus, plus, positive, positive, that's in the first quadrant, right? If it's positive, negative, the x value is positive, the y value is negative, what quadrant are you going to be in? A fourth, right? It wants quadrant 4. So which y value for point P do I need to choose? Negative 1/2. Okay, that's why they tell me in quadrant 4. Whenever, guys, throughout the entire course, whenever they give you like a little additional information, like it's existing in quadrant 2 or 3 or 4, or cosine's positive or sine is negative, something like that, that is vital information. You just can't ignore it, okay? If you could just ignore it, they wouldn't write it. Does that make sense? Okay, so that quadrant 4 is essential to the problem. The other stuff down here, we start talking about terminal points on the unit circle. That's exactly what I was trying to show you with GeoGebra. Those red arcs, guys, those are a distance, right? And we're going to use the letter T to represent those because they're associated with the terminal point, okay? So the arc of T equals pi over 2 is associated with the terminal point 0, 1, okay? So that's why we use T. Now, here's the thing. That theta right there, does anybody know what that angle theta is? Pi over 2 as well, right? So theta equals the same as T. It equals the same as pi over 2 in this situation, which then associates itself with the point 0, 1. If I go to the second picture, that theta, the angle that would be traced out there, would be pi, right? The distance walking along the arc of, or the semicircle in this case, of that unit circle would be pi. They're the same. The terminal point associated with it is negative 1, 0. 3 pi over 2. The terminal point there is 0, negative 1, and then 2 pi would be 1, 0. Those a lot of times are referred to as your quadrantal angles, okay, if I'm referring to theta, okay, because they delineate the interchange from quadrant 1 to 2 to 3 to 4. Does that make sense? When we are working with the unit circle, why do we have the unit circle? And it's all going to kind of play out in the next couple of days, but I want you guys to take your calculator real quick. Type in cosine of pi over 2. Make sure you're in radians. Type in cosine of pi over 2. Tell me what you got. You got 0. Is 0 one of the coordinates for that point that's associated with pi over 2 in the unit circle? Okay. Type in cosine of pi. Negative 1. Is negative 1 one of the coordinates of the point associated with the terminal point of pi on the unit circle? Type in 3 pi over 2. Got a 0, right? It's one of those coordinates for that point associated with 3 pi over 2. What are you going to get? Don't even do it. What are you going to get when you put 2 pi in? 1. You're going to get 1. So what's the pattern here? What are we seeing here? The cosine is the x value. Okay? Cosine ends up being the x value of the terminal point. What do you think the y value is going to be? Sine. Okay? Now think about this, and we're going to see this in a couple questions later on, or a couple slides below this. If I'm in the unit circle here, thinking about just any theta, that's 1, right? My theta I'm talking about would be that angle right there. This would be x. This would be y. If r is 1, let's think about cosine. Cosine of that theta. We have talked about in chapter 5, cosine is adjacent divided by hypotenuse, right? Okay. If it's adjacent divided by hypotenuse, and we're in the coordinate plane right here, the adjacent is x. The hypotenuse is r, right? Or the radius of your circle. But what is our r in this case? 1. So I get x over 1. Well, that tells me cosine theta then in the unit circle is just x, right? Of the point that's on the circle. That makes sense? Cosine theta equals x. So I can do the same thing. Sine of theta would equal y. And I'll talk about that. We'll see that show up again later on. But this is the benefit of being able to talk about and use the unit circle. Okay. Tomorrow we'll again, and we'll talk about reference points, reference terminal points, which is going to be analogous to what we talked about in chapter 5 about reference angles. Okay. And we're going to spend a lot of time working with radians and only radians because we just need to just drill that into our mind and be able to know that when I say pi over 6 radians, you know automatically 30 degrees. When I say 5 pi over 6 radians, you automatically know I'm talking about 150 degrees, okay? So those are things that we want to be able to do kind of instinctively. So forcing you to deal with radians, I think, will help train you to do that. I'm not going to post anything on WebAssign today. We'll work a little bit further tomorrow, and then by the end of tomorrow, we should have enough stuff to move through an assignment. Okay?